So I hear you guys have already discussed the origins or the development of the model of the atom. So I'm going to be super, super quick because I don't want to hash over stuff that you've already talked about. But it all began long, long time ago, like in the years BC, with this dude. Named Democritus. And Democritus, in the year like 400 BC or thereabouts, was sitting around with the other dudes that were sitting there, the Greek philosophers, and they were doing what they did. They sat around and they talked. And they said they didn't experiment or anything else. They just talked and they said, I wonder what. And he said, I wonder what. I wonder if there isn't some smallest piece of matter. And he says, you know what? I think there does have to be. If we took this statue and we kept breaking it into smaller and smaller pieces, I know there had to be something that is the smallest piece. So he hypothesized and stated that there must be some smallest piece of matter. And that smallest piece of matter surely must be both indivisible and indestructible. And so he called it atomos, which is from the Greek. That means such. And so things bebop along for many, many years, like 2,200 years or thereabouts, until the very early 1800s, which was like 1801 or thereabouts, when a guy named John Dalton this is around 1801 or thereabouts, says, I found it. He discovered the atom. And what he said about the atom is that it's tiny, it's super hard, it is indivisible, and it's indestructible. That's what he said. And he named it atom after Democritus, in honor of what Democritus said. So his says that his model said that an atom is super, super tiny, and it's like a marble or a ball bearing. So it's small, it's spherical. Oops, I can't spell spherical. SPH. And it's dense, like a marble or BB. He also said lots of other important things that we now know as Dalton's atomic theory. Most of his statements of his atomic theory still hold true today. I want you to please read those statements of his atomic theory that are on page 102 of the text, or you can Google it, Dalton's atomic theory. All right, and I want you to know the general idea of what they said, because most still hold true today. And why do we keep it if some of it's still false? We keep it because most of it still holds true today. And because his great-great-great-grandkids, they deserve, that was their grandpa. All right. Then, for nearly 100 years, Dalton's model holds. And then in 1897, a dude named J.J. Thomson comes along, and he discovers the electron. He did it using what's called a cathode ray tube, and so now our model changes. Now it's not this hard, tiny sphere anymore. Now Dalton came up with what he called the plum pudding model. And we don't have plum pudding here in the United States, but we do have chocolate chip cookies. And I can liken plum pudding to chocolate chip cookie dough. And so he imagined that an atom was like this, where this part right here was like dough, uncooked chocolate chip cookie dough, and that this part was here positively charged. And then you took that dough and you threw chocolate chips in there, and wherever they landed, they're of course negatively charged, wherever they landed they stuck, because the doughy part was sticky and positively charged. And so since opposites attract, it's going to stick in that dough and stay there. And this was his model of the atom, the plum pudding model. It did not stay around for very long, because a lot of things were discovered pretty quickly after that. Protons were discovered, and then very, very soon after, neutrons were discovered very soon after, and then the nucleus was discovered. This was in 1911. A dude named Ernest Rutherford, who was actually a teacher, a very well-respected college professor, and he decided he wanted to take a picture with this new fluorescent material, and so he put a piece of gold foil and he shot a laser beam at this gold foil, and he said, well, this will slow it down and go right through here, and we'll catch on this fluorescent material. This is on page, by the way, 107 of your text, and you can see it go right through there. This gold is very heavy. It'll slow it down and it'll take a picture. But the experiment is the most famous of all the failed experiments ever, because it didn't give the results that they thought it would. And instead of these atoms, this laser beam going straight through like you thought it would and landing on the back, they kept bouncing back. Now, most of them did go through, but a lot of them did not. And they would bounce back and hit. Some of them ricocheted. And they said, what in this world is making that happen? And so Ernest Rutherford said, there must be something inside an atom that laser beam is hitting, that those alpha particles are hitting and making it bounce back. And so he made some postulations about that, and he said, there's got to be something, and it must be in the middle of the atom, hence the name nucleus. It must be tiny, because most of the laser beam particles, those alpha particles, are going through. And it must be really, really hard, because it's hard enough that those alpha particles, when that laser beam hits it, are bouncing back. So he discovered the nucleus with this very famous gold foil experiment. So even when we fail as scientists, we still are going to take our results from our experimentation and say, okay, what is a reasonable explanation for these results? And we learn from them, just like Rutherford. So this was his model. So now we have this tiny, tiny center called the nucleus within our atom, and he postulated that we still have these electrons out here and the doughy mass and so forth, but we have a nucleus now. All right? Then one of his students, whose name was Niels Bohr, who is Danish, he said, well, wait just a minute. He worked with Rutherford for a long time. He said, wait just a minute. These electrons are not going to just be sitting there. They have way too much energy, lots of energy. They're going to be moving. So he postulated that they have not just are moving, but they have their own discrete amounts of energy. So now we have our nucleus, and then we have these electrons, he said, and they're moving, and I can't draw it, and I'm not going to try, but I want you to imagine with me a Jimmy Neutron. You know, one that's going like this and like this. Yeah, that's what I'm trying to draw. That's what he imagined it was, but in their discrete energy levels. That's what he said. Okay? So he said, electrons orbit the nucleus in energy levels. And then finally we have our most current model. It's called the quantum mechanical model. Oh, I can't seem to spell. And that quantum model says that, yes, those electrons are moving in these energy levels, but they're moving so fast that it's not like a planet that you can follow with your pencil. It's like a smear or a cloud. In it. And that's what that says. And this dude's name was Schrodinger, and there was lots of others as well. There's your quantum mechanical model. I'll have a quiz on these. I don't care so much that you know the dates, but I do very much care that you know the players who was involved in this and what their model looked like. Be expecting a quiz and a test. Have a great week.